All right, good people. Welcome to part 2 of 6.6. This is actually the third video, but it kind of gives us some consequences of understanding that the definite integral is the area accumulation under the curve. And so we're going to talk about some properties in terms of symbols, and then we'll explore them through the graphical examples that we have. There's actually 4 properties that we're going to talk about. We're going to do the first 2 in this video. We'll do the second 2 in the second video, and then that'll be the end of section 6.6. So here's property number 1, and it's written in symbols, and I need us to read it and see if we can understand what it's trying to tell us. Property number 1 says, if you're taking the integral of f of x dx from a to b, that equals the negative or opposite of the integral of f of x dx from b to a. So what happened? What happened with these symbols? What's different? Well, this is saying if my limits of integration happen to, and here let me use 2 different colors. If my limits of integration happen to switch, then I can find the integral because I know that those 2 integrals are just opposites of each other. So when I switch my limits of integration, I get the opposite answer of what I'm given, of what I start with, I guess. And so the question is, why does it work? And then why is it important? Well, it's important because we usually try to find definite integrals by starting with the smaller number on the bottom of the limit of the integrand. And one of the reasons why we want to start with the smaller number on the bottom is because we want to go from left to right, so that we can find the area in a normal manner. So if you think of it that way, that if my b value is the larger value, and I'm starting from the larger value to the smaller value, well, then I'm going backwards. And if I'm going backwards, well, then I have to have an opposite accumulation. So when I look at these 3 examples of these 3 definite integrals, the question is, are any of them set up to where the bottom limit is not the smaller limit? When I look at letter A, this is the limit of the integral, or the integral of f of x dx from 1 to 5. So that's a normal setup for a definite integral. But letter B, I'm looking for the integral of f of x dx from 3 to negative 2. So what I could do is I could say, hey, this is the same thing as the opposite of the integral from negative 2 to 3. So when I switch the limits of integration, those numbers at the bottom and the top, when I switch them, I get the opposite answer for the definite integral. And then, is this set up normally, or is this set up backward? I think this is set up backwards. A smaller number is not on the bottom. So I can say, hey, this is the same thing as the opposite of the integral from negative 2 to 9 of f of x dx. And so I have my 3 integrals written so that I'm going from left to right, and I can find the areas of these in a familiar manner. So I'm going to find the area from 1 to 5, from 1 to 5, from 1 to 5. Okay, well, that means I got to be careful because this area here is going to be positive, right? But this area here is going to be negative because it's under the x-axis. So the negative accumulation because it's under the x-axis. So I'm going to break this up into 2 parts. I'm going to do the blue part first. This is the area of a triangle. So that's 1/2 base times height. And then plus, this is also the area of a triangle. But it's not plus, actually, it's minus because it's on the bottom. I'm subtracting it. And the base is 2, so it's 1/2 2 times the height, and the height is 2 as well. Oh, well, what do you notice? This is just going to give me 2 minus 2, and that's just going to be 0. So integral letter A is 0 because I have positive accumulation, and then I have negative accumulation, and they're the exact same size, so they're going to cancel each other out. And that's something that usually pops up on the exam of a way to save time is to look for some symmetries in the areas, because if you have an area that's positive and an area that's negative, you don't need to calculate it. You can see, oh, those are going to cancel each other out because they're the exact same value, except one's positive and one's negative. Okay, A is out of the way. Let's look at B. When I look at B, now we're going from -2 to 3. From -2, let me do it in a different color. Let's do this one. From -2 to 3. But because I switched the limits, I'm taking the opposite of that area. Well, I already found this part is 2. So really all I need to do is find out what this part is and then add it to 2. Right? So I'm starting from -2 all the way to 3. But don't forget, because I switched them from the original setup, this is the opposite. So it's the negative of whatever I get. Well, I notice that this, I don't know what color this is, but it's going to be positive, this triangle. And it's a triangle, so it's 1/2 base 1, 2, 3 times height. So 1/2 base times height plus the other part, which we had already figured out in letter A. And I can put these two together and I can get an answer, right? So this first triangle, I think, is going to give me 3 plus 5 plus 2 is going to give me 5. But it's opposite because I'm going backwards. The original integral was going backwards. I was starting at 3 and going backwards to -2. So therefore, my answer is going to be the opposite of what I would have gotten if I started at -2 and went forwards to 3. So my answer is -5. Okay. So far, so good. And now we go to letter C. Letter C, we flipped it. Now we're starting at -2. So we're starting here, and we're going to 9. We're ending where the graph ends over here. I think we found almost all of them except this piece and this piece down here, although I see that this is symmetrical to the one right next to it. So if this was -2, then this is also going to be -2, right? So then I can say this equals the opposite of the first greenish part, which we said was 3, plus the bluish part, which we said was 2, minus this part, which is negative because it's under the x-axis. And this was -2 plus another -2, so that's going to be -4, plus the final part that I haven't figured out over here, but that's another triangle, so it's going to be 1/2 base times height. So 1/2 2 times 2, which is just 2. And that's what I need to figure this out. So I'm trying to color code so that you can see where all these numbers came from. The first area, 3. The second area, 2 in blue. The third area is both of these orange triangles that became one big orange triangle, -4, and then +2 over here. So if I go from left to right, that's what it would be. But remember, the original integral was going backwards, so whatever I get in the bracket, I have to take the opposite of that. What do I get in the bracket? Well, I notice that if I add 2 and 2, I get 4 minus 4, that's gone, so I'm just left with 3, and because this was going backwards, this is -3. So one of the two properties is if I have a switch, whenever I switch my limits of integration, I'm actually switching the direction, so I'm going to get the opposite answer. So if the denominator is not the smaller value, go ahead and switch it, but understand that your answer is going to be the opposite of that. That would be property number 1. Property number 2 is fairly easy, and we'll end this video with property number 2. Property number 2 says if you're multiplying a constant times a function and taking the integral of that, I can pull out the constant, do the definite integral, and then multiply the constant back in. Kind of reminds us of the constant multiple rule in derivatives, right? Like if I was multiplying 3 times tangent x and I wanted to find the derivative of that, I could hold the 3, take the derivative of tangent x, and then multiply the 3 back. That's the exact same idea for property number 2. Why does it work? Well, because when we multiply by a constant, remember graphically it stretches everything. So that means everything's going to be 3 times as far away from the x-axis as it was originally. So if we just find the original amount, we can then just multiply by that factor that got the graph stretched. So when I look at letter A, and by the way, we're still using the same graph up there. When I look at letter A, this is the same thing as 3 times the integral from 2 to 5 of f of x dx, which means I need to find the area between 2 and 5. Well, the area between 2 and 5, we had already found. Oh, no, we hadn't found. Okay, well then we need to find it from 2 to 5. Well, I know this one is negative 2. I don't know what this one is, but it looks like it's a little triangle, 1/2 times 1 times 1. So that's positive 1/2. So I'm going to say that this equals 3 times this little triangle is going to be 1/2 minus the orange part, which was 2, or negative 2. Or you can add a negative 2 if you want to think of it that way. So that's 1/2 minus 2. 1/2 is the little blue part, minus 2 is the negative accumulation under the x-axis in orange. Put those together and then triple it, and you're done. Let's see. So that would be 3 times negative 1.5. And I believe that's negative 4.5. My answer is right there. That's it. What about letter C? So a couple of things about letter C. Notice that I have a negative, so I can treat that as a negative 1, and I can take it out of the integral. But then my integral is upside down because my limits are backwards. So that means I'm going to have to take the negative of whatever's there because I'm going to reverse them to put them in a quote-unquote normal position to go from left to right. But when I do that, I have to take the negative of whatever was there, which means it's going to become positive. So the negative I got by pulling that negative out of the integrand, but it became positive because I switched the limits of integration. And now when I come back and I look at negative 2 to 7, negative 2 to 7, that would be from here, negative 2 to 7 over here. I think we found all those values. Awesome. So then all I have to do is put those values together, and those values are just going to be their normal values because my limits are now correctly set up to go from left to right, and my integral is positive. I don't have to worry about changing the sign. So this first triangle, I believe, was 3. The blue triangle was 2. And then the orange part was minus 4. And I think that's where it ends. So if I can put all of these together, I have my answer. And my answer is 1. So these two properties, one of them says if my limit of integration is upside down, meaning that the bottom number is not the smaller number, you can flip it, but that's going to take the opposite answer. And then the second property says if you're multiplying by a constant, I can pull out that constant, which I'm about to do here with letter B. I can pull out that constant. Everything stays the same, and you can find the definite integral however you normally find the definite integral and go from there. Letter B turns out my limits are still upside down, so I can fix them, quote unquote fix them, by putting the smaller value on the bottom. But then I have to take the opposite of this, so that's going to give me positive 4, and then you can proceed from there. By the way, I think this would be an easy one to figure out because we already did from negative 2 to 0. Negative 2, oh, we didn't do negative 2 to 0. We did negative 2 to 1. So we would have to find this little triangle. I think I'm running out of colors. I would have to find this little triangle right here and then multiply by 4, and then that'll be it. So 1/2 base 2 times height. Oh, what is the height? I like this problem. Did I set it up correctly? Negative 2 to 0. Yeah. Negative 2 to 0. What's the problem here? I don't know what the height is there because it's not 1.5. How can I figure out what that is? We'll talk about it in the next video because this video is going a little bit long. So we'll talk about how to get to that one first thing on the next video.